Okay, are there any questions?
Oh wait, so on the calendar that we're doing chapter 14 and then 19, but then on the homework page like chapter 19 first and then chapter 14. So which one are we doing first?
14.
14.
That's a mistake.
Oh, so we're not going to do the chapter 14 and 19 together as one exam?
No,
Oh, okay.
two separate
So
exams.
14 chapter is due this Thursday, right?
No, we're not having the test this Thursday. Are we?
Oh, cool.
I haven't finished chapter 14 yet, and so after I finish chapter 14, then we'll have the test, well, per usual. Okay, let's talk about, well, any other questions? All right, let's talk about the kinetics here. Where did we leave off last time?
A modified method of initial
Use a
rate.
lot of that.
Okay, that's for the lab. We talked about that. Yeah. I think we were talking about the rate law. You know, if I have a rate law, A plus BB plus dot dot dot, this goes to product, then the rate law is going to equal K, A to the M, B to the N, etc. And so the question came up, what is the origin of M, N, and K?
Oh yeah, you said potential collisions.
Okay. And where do these come from?
Yeah, we did that.
We did it?
Yeah,
Okay.
with like all the arrows.
Right. So we talked about M and N. They come from like simple collisions. We talked about methane combustion.
Yeah.
Yeah.
So if we know the collision, then it is easy to determine. M and N. And so it boils down to this. If we have a simple or elementary process, then the rate law is just going to be based on the coefficient. So let's say I had A plus BB, etc., goes to product. The rate is just equal to K, A to the little a, B to the little b, here. And so there is a connection here between the coefficient and the order. The reason we couldn't see the connection earlier is because we don't know if it's a multi-step or one-step. And so the example here is this. CH4 plus 2O2 gas goes to product. If this is one step, then the rate is very simple. The rate is equal to K times the CH4 to the first and the O2 to the second. And so what I have to have is I have to have a coordinated collision. One methane and two oxygens have to collide in sync. If, on the other hand, it's multi-step, then we don't know because the rate is just going to equal K times the CH4 to the M, O2 to to the n. Because in a multi-step, what we have to do is we have to break it down into individual collisions. So here, each step is an individual collision. And the rate is just going to equal K, whatever is involved, AA, BB. And so the rate of the step, and then we must determine the slowest step. And so we just look, which of these is the slowest. Then the overall reaction rate, so we'll just say the overall rate is equal to the rate of the slowest step. The slowest step is called the RDS. RDS stands for rate determining step. And so it's the bottleneck in the steps. So let's look at an example here. A simpler example from the book. Two NOs plus an O2 yields 2 NO2 gas. 2 NOs plus an O2 yields 2 NO2. All these are gases, so I'll leave it off here. And so if this were one step, then the rate law is pretty simple. The rate law for this step is equal to the rate of the overall reaction, which is equal to K times the NO. Now we need two NO molecules to sync their pack, so it's going to depend on the left NO and the right NO. So if we double the NO, then there should be a square dependence. So it would be NO squared times the O2 concentration. Here. How do we know if it's a one-step process or not? Well, two things. One is that, the reaction has to match, and two, the rate law has to match. And so it has to match with the experiment. And so the experimental rate law is given. And so the rate, as determined by whatever method they used, came out to be NO squared times the O2 concentration to the first. And so when you look at this, then it looks good, right? Because when we look at this one, this would match this. These two match. Therefore, this mechanism, one-step mechanism, is consistent with experiment. One, the net reaction is the same. And two, the rate law for the RDS equals the overall rate law. In other words, the experimental But the problem is this. But these tri-molecular, these are also called termolecular collisions, have low probability, or have a lower probability. I mean, they still can occur, but the probability is not very high. Basically, what has to happen is this. You know, you got an O2 here, and then an NO comes in this way, and an NO comes in this way. So it has to be a coordinated collision. Everything has to line up perfectly so that these three molecules collide at the same instant of time. But actually, have a lower probability, which does not match how fast this reaction occurs. And so this NO is a product of when we use nitric acid as an oxidizer. When we use nitric acid as an oxidizer, it produces NO, which is colorless. And the NO is oxidized by air, O2 and air, and it immediately produces a brown gas. So when you use nitric acid in a lot of redox reactions, you produce this brown gas, fuming gas, immediately. And since this happens so fast, it's likely that maybe it's not just one simple three-molecule collision. And so we're going to continue here with this. Are there other mechanisms that are also consistent? With experiment? And the answer is yes, there are. And so rather than doing a termolecular or trimolecular collision, let's try a bimolecular collision. Or a unimolecular collision. Did I talk about bimolecular, unimolecular?
No.
No? I better talk about that. All right, unimolecular is like this. How can you have a unimolecular collision? Uni would just be one molecule colliding. And so is that possible to have a one molecule collision?
H2O.
It doesn't seem possible. H2 would?
H2O with H2O.
Well, that would be a bimolecular because you'd need two molecules. One molecule of H2O plus another molecule of H2O.
Would it be a reverse reaction?
It could, but let's just look in the forward direction. A unimolecular collision would be something like this, where A collides with a wall or an inert, that is, unreactive molecule, maybe nitrogen or something like that. And so if it's a unimolecular collision like this, then the rate is pretty simple because the rate for this would be, these are called simple collisions. The rate for this is going to equal Ka to some order dependence. Now, if I double the amount of A, will the number of collisions not change? Will the number of collisions double, or will the number of collisions quadruple? What do you think? If I double the A? Yeah, it should double, so this is going to be first order in A. well, unimolecular is just first order. So A goes to whatever. It's just, bimolecular involves two molecules. In a bimolecular collision, we'd need an A colliding with an A, and this would go to something. In other words, we have 2A goes to whatever. And so the rate here will depend on both A's, the left A and the right A. But, A is the same, so if I double the concentration of A, then the left A doubles and the right A doubles. And so if the left A doubles, we double the collisions. If the right A doubles, we double the collisions. And so if both A's double, we're going to quadruple. And so it's going to be A squared. And so do you see the coefficient 2A gives us 2 here. Or it doesn't have to be the same molecule. It could be A colliding with a B. If A collides with a B, then that's also bimolecular. And the rate would be Ka. It'd have to be first order in A. So if I double A, the collisions double. And it has to be first order in B and second order overall. And so what about a trimolecular? Or termolecular collision?
It would be A plus B plus C.
Yeah, right. We'd have something like A plus A plus A, or A plus B plus C. Here, A plus A plus A is just 3A, right? And so if I have something like this, goes to product, the rate is going to depend on the left A, the middle A, and the right A. And if all of those double, then, so it'll look like this, Ka to the third. This would be first order in A, first order in B, first order in C. What if I had something like this, A plus B? This would be second order in A and first order in B. And so if it's a simple collision, then it's easy to figure out, what the order with respect to each concentration is, because it just has to be governed by the collisions. All right, so these termoleculars are going to be less probable because, if you had a million collisions, what fraction do you expect would collide like this? A three-way collision that happens to... Oh, it's going to be a very small fraction. So bimolecular collisions are much more common. So let's try a bimolecular collision. If we have a bimolecular collision, then we just take two molecules. Maybe it's one NO colliding with another NO. Or what's the other choice? The other choice, I only have one more choice, is an NO colliding with a O2. And so these are potential bimolecular collisions here. All right, actually I started with the wrong one, but that's okay. So NO colliding with an NO, or NO colliding with an O2. Now, this is going to occur multi-step. This would have to be multi-step because I wouldn't be able to do it in one step. And so if it's multi-step, we'll just start off with step one. And I don't know which one, looks more reasonable, but let's try to figure out some products here. If an NO collides with an NO, what might you form? You might form something like N2 and O2. Have two NOs collide, form nitrogen and oxygen. That seems reasonable, but the problem is if this were step one, then step two is going to be very tough because is nitrogen and oxygen very reactive necessarily? No. And are either of these product here? No. And so this one doesn't seem so promising. What else could we generate? Well, we might generate something like this. An NO2 and an N. Does that seem so promising there? Not really. This atomic nitrogen doesn't seem so promising. What else? We might generate an N2O and an O. N2O is, have you heard of N2O before? N2O is nitrous oxide. And so maybe that is more promising. And oxygen? Oxygen, that would be atomic oxygen. Atomic oxygen, have you heard? Atomic oxygen can be produced. You know, this is called a free radical. Atomic nitrogen, less so, because atomic nitrogen usually come from molecular nitrogen. Molecular nitrogen has a nitrogen-nitrogen triple bond, very strong. But this would be atomic oxygen. And maybe that works. Or others. It might, be something like this, where the two molecules dimerize. They come together and form a link, and they'll form an N2O2. Have you heard of N2O2 before? Yeah, probably in your homework. And so maybe this sounds pretty promising here, an N2O2. Maybe the next most promising might be something like this, but getting from this to that might be difficult. This because of atomic nitrogen, that would be tough. Well, let's look at this one here. An NO plus an O2. What might that result in?
NO2 with an atomic oxygen.
Yeah, NO2 with an atomic oxygen. Wow, this looks pretty good, right? Looks promising. Or how about this? Would you think you'd form maybe N3 minus, nitride ion, plus oxide? Could that be feasible? You think? No, this one's impossible because we have to look at the charge. Over here, the charge is neutral and neutral, so the total charge here is 0, but the total charge here is -7. And so apparently we just gained 7 electrons out of thin air. And so this is not possible. We could gain some electrons and lose some electrons, but that would complicate things. And so we start off with the first step. Which of these looks the most promising to you as a first step?
NO2 plus O.
NO2 plus O. This one? All right, let's try that one. So we're just going to say our first step is going to be NO plus O2 yields NO2 plus O. Sorry, let me just take care of this. This is a product, but what is this? This is something we call an intermediate product. Intermediate. Intermediate, is not going to stick around here, but let's just take a look at the rate. If this is a simple one-step collision, and so these would all be simple collisions here. Nothing hidden. Then the rate is just going to equal K times the NO to the first, O2 to the first. And so we look at this rate law, it doesn't match. But we're not done yet because we can't have an intermediate sticking around. The intermediate has to undergo further reactions. And so in step 2, we need to react that intermediate. The intermediate is going to be reacting with the other NO. So we have an O plus NO. This is going to yield NO2. And that's going to consume the intermediate. And so the rate for this next step looks like this. The rate is equal to K
It's going to be first order in O and first order in NO. And so we look at both these, and we pick this one. If we pick step 1 as slow, we say that this is the rate determining step. Does the rate law match our experimental rate law? No. You see, it doesn't match because our experimental rate law is fact. And so it's a fact that it's second order in NO. Here, this just shows a first order NO dependence. And so it cannot be step 1 as the slow step here. What about step 2 as a slow step? If we do step 2 as a slow step, then still doesn't match. But the problem is this. The rate law can't have the intermediate in there. When we mix the chemicals up, we aren't mixing atomic oxygen in there. And so we have to get rid of the intermediate. Let's just say remove the intermediate. So how do we remove the intermediate from the rate law? There are two ways that we can remove it. One is called the fast reversible approximation. The other is called the steady state approximation. All right, so for fast reversible, let's look at that first. We assume that step 1 is fast and reversible. And so what this is going to look like is this. For step 1, we have NO plus O2 yields NO2 plus O. If we make it reversible, we'll just draw these two equilibrium arrows like that. And then we'll say that there's a forward rate, which is going to depend on K1, and a reverse rate that's going to depend on K minus 1. And so we'll say that the rate of the forward reaction is equal to the rate of the reverse reaction. The forward reaction is going to depend on K1, and it's going to be first order in NO and first order in O2. The rate of the reverse reaction here is going to depend on K minus 1, and that's going to be the NO2 concentration first order and first order in O. Then what we'll do is we'll solve for the intermediate concentration. So the intermediate concentration will equal K1 over K minus 1 times the NO times the O2 divided by the NO2. All right, then we're going to substitute. So this is rate for step 2. Rate for step 2 was equal to, actually what was step 2 again? Step 2 was O plus NO yields NO2. And we're going to call this K2 for step 2. And so the rate was K2 times O NO. And so the rate is going to equal K2. Now substituting this for O, I'm going to get K1 over K minus 1 NO O2 divided by the NO2 times the NO. And so what I'll do is I'll combine these constants and call it K prime. So K prime is just K2 times K1 divided by K minus 1. And then I'm going to combine the two NO. So this is going to be NO second order, O2 first order. But NO2 is in there. NO2, you know what order it is? -1 order. And so this is product. And so what this reaction is saying is as the product concentration builds up, it's going to slow down the reaction. So this is some kind of negative feedback there. And so does this rate law match? Doesn't match. Therefore, this mechanism is not consistent. It didn't work. All right, it didn't work, so let's try a different step one. I'll pick another collision that might look promising.
N2O2.
N2O2. And so that was NO plus NO. This will be step one. Yields N2O2. N2O2 is an intermediate, so that's going to go further reaction in step two. Step two would be N2O2 plus, I just have an O2 left, and this would give me NO2. And so if I take these two steps and add them together, I'm going to get the net reaction, 2 NOs plus O2 yields NO2. 2 NO2s. So the net. And so the sum of the steps of the mechanism must equal the net overall reaction, which it does. And then we look at the rates. The rate based on the first step would just be K1 NO squared. And so here, this tells us it can't be, the bottleneck or the slow step can't be the first step. The slow step is always going to dictate the overall rate of the reaction because it doesn't matter how fast you can go before or after. Once you hit that slow step, then everybody's going to be reduced to the same speed. And so here, N2O2 plus O2, well, let's take a look at the rate for this. If I look at the rate for step 2, the rate for step 2 is going to equal K2 times the N2O2 concentration to the first times the O2 concentration to the first, right? All right, so what you should do is try using the fast reversible assumption to get rid of the intermediate N2O2. So we can't have this. And so what we're going to say is this one's slow didn't work out. It was inconsistent. And so that leaves us with this one's slow. But we don't know if it's inconsistent or not because we have intermediate here. And we must get rid of the intermediate. And so how do you get rid of the intermediate? And so just try to use the fast reversible assumption to get rid of the intermediate here.
This is our solutions.
No, they're not. He just said it. Maybe he does not pay attention. Oh, no, he wasn't laughing. Oh, okay. He said if you start finding it, it's only 14. Next week. Next week? If he finishes this week, then it's probably next week. It's just not this week. Yeah.
Oh, yeah, yeah, I got an 80, I think I got an 84 on the lecture, on the first lecture test.
What's your big goal of stuff? Papers on what you call it. Tuesdays and Thursdays. Well, you had some on Wednesday last week. Yeah. It was my smallest thing, yeah. What I got going. So healthy. That's not my opinion, but okay.
I was at the sports city at 7:90, which was like green stuff. Because you can do like all this green stuff.
You have class after this?
No.
Oh, but you go home?
No, for that, no, I go to the workshop.
Oh.
He said,
Well, then, if there's stuff in your mouth, I'm not gonna tell you.
I have my phone on me, so I'm gonna check my phone.
Okay.
the fast forward, the fast reversible.
Did anyone get it?
Yeah,
Yeah, what did you get?
the K prime NO squared and concentration of O2 to the first.
Oh, okay. So if we get rid of the intermediate, we end up with this rate law. And so what we can say here is that this mechanism is consistent with experiment. This mechanism is consistent with experiment, but does it prove this mechanism is correct? The problem is we can't prove this because there might be other mechanisms that are consistent. So we can't prove without additional experiments. An additional experiment, for example, would be the detection the intermediate N2O2. You know, if we did an experiment where we could detect the presence of N2O2, you know, as it's being formed and consumed, then maybe, yeah, that would be pretty good evidence that this would, or this could be it. But we can't prove without additional, for example, therefore, all we can say is that it is consistent. There could be other mechanisms that are also consistent. All right, let's try another example. I'll talk about the other method of getting rid of the intermediate a little bit later. This next example is also from the book, just straight out of the book. It says H2 plus ICl yields HI plus HCl, right? Nope, sorry. I think it would do that, but it's not. It's 2 ICLs. This is going to yield I2 plus 2 HCl. Okay, that's right. This is a redox reaction. And the first thing they tell us is the experimental rate law. The experimental rate law is fast. And so the experimental rate law is the rate is equal to K times the H2, it's first order in H2 and first order in ICl. H2 first, ICL first. Could this happen as one step? Is it possible? No. And so based on this rate law, a one-step mechanism can be ruled out. Not possible. If it was a one-step mechanism, then it should be second order in ICL. First order in H2. And so it's not a trimolecular. Rather than trimolecular, termolecular, maybe let's try a bimolecular. And so try a bimolecular collision. And so we only have two choices for bimolecular, an H2 plus an ICl or an ICl plus an ICL. Uh-huh.
Is it supposed to be second order on ICL or not?
No, it's first order. That came from experiment. If this were one step, then it would be second order in ICL. Well, here they just tell us. You know, it came from experiment, so this is given. I didn't derive this. You know, otherwise I would just have to write M and N because I don't know. And leave it at that. But somebody already figured it out using method of initial rates or pseudo M order or whatever else, and they came up that it's first order in both of these. And so you would have had been told that. Otherwise, I don't know what it would be. Well, let's take a look at these two collisions and come up with potential products for the collisions. For example, if H2 and ICl react, if there's a collision between these two, what might form? HCl and HI? Yeah, that sounds pretty good. You know, those are reasonable. HI and HCl. How about some?
Is that reasonable though? Because aren't they strong acids?
They're strong acids, but this is not an acid-base reaction. What kind of reaction would this be? This would be a redox reaction. If we look at the oxidation states, hydrogen, elemental form, so it's 0. And then these, which one do we assign first, iodine or chlorine? Chlorine is more electronegative, we get -1. So if chlorine's -1, iodine would be +1. And so what's happening here is hydrogen's losing electrons to iodine. And so iodine gains 1 electron, it goes to 0. Iodine gains 2 electrons, it goes to -1, which is what we have here. +1, -1. So those are redox reactions. What's the oxidizing agent? What's the reducing agent?
ICL is reducing.
Well, actually, it would be giving up electrons would be the reducing agent. So H2 is the reducing agent. ICL is the oxidizing agent because iodine is picking up electrons in ICL. Chlorine, nothing happens to, because chlorine stays the same. And so if I think, you know, compared to these, you know, which one do you think is a stronger oxidizer reducer? H2ICL versus HCl. You know, which one do you think combusts more easily, hydrogen gas or hydrogen iodide? If you compare the two, which one do you think you could burn easier? Hydrogen gas burns easier or HI? Hydrogen gas. And so in terms of redox, the driving force is different. So this, I see no problem with this. This looks fine. I see problems with this. You know, if people started doing something like this, then this is going to form H2I plus Cl minus. You know, something like this makes no sense because you know, Cl minus, and this is neutral, so it gives us a net -1 charge. This is neutral here, so we're getting an extra electron in here. And then H2I, I mean, could you draw the Lewis structure? Not really. H2O, no problem. H2S, but H2I, it just doesn't make sense. And so, left. Can you think of anything else? Not really. All right, let's take a look at this other collision. What would we form here? Yeah, maybe it's Cl2 and a I2. Does that look reasonable? Yeah, this is a reasonable collision here as well. You know, because we know chlorine, we know iodine. How about something like this? ICl, ICl, you know, ICl, ICL. Really. But yeah, this looks okay. Now, what do you think is more reactive here? Cl2 and I2 or 2 ICLs? Yeah, probably Cl2. Chlorine is fairly reactive. And so this looks like the most stable, doesn't it? So maybe this one we should start with, because this product looks... Let's go ahead and do that. So if we have an H2 plus ICl, this yields HI plus HCl. We'll call this step 1. All right, we're going to have an intermediate, HI. We need to get rid of that intermediate. We don't have any HI in the product over there. And so step 2, let's get rid of it. So HI will react with what we have left over, ICL, to produce I2 and HCl. This is good because if I add these two up, the intermediate cancels out and I end up with the net reaction. H2 plus 2 ICLs yields I2 plus 2 HCl's. And so the net reaction matches. Now, we just have to make sure the rate law matches. And so if I let's call the first step the slow step. If I call the first step the slow step, then the rate is going to equal K1 times the to the first and the
ICLs.
to the first. Well, if I call the first step the slow step, take a look. This, you know, the rate for the RDS here matches experiment. And so I don't have to go any further. Because if this is the slow step, then the reaction can't go any faster than its slowest step. This will be the rate of the overall reaction. And so it turns out that this mechanism is consistent with experiment. And so we're done with this. I don't care how fast or how slow step, well, I do care how slow it is. I don't care how fast step 2 is, as long as it's faster. And it's going to have no impact on the rate. And so this was a lot quicker here. All right, that's how to get M and N. What about K? And so we were able to determine M and N by looking at the elementary or the simple collision in the slowest step. Then we get it directly from the coefficients here, 1 and 1. Now, what does K depend on? Let's look at that next. K, the rate constant, is given by the Arrhenius equation. As A e to the minus EA over RT. And so A is called the collision frequency. Collision frequency is, you know, how frequently do those successful collisions occur? This EA is called the activation energy. R is just a gas constant, 8.3145 joules per mole Kelvin. T is just your temp, Kelvin temperature. And so the rate constant depends on collision frequency. The more frequent the collision, the bigger the rate constant, the faster the reaction. It depends on the activation energy. And so let me talk about what is the activation energy and how does that depend on temperature. And so we'll take a look at this reaction that we just looked at here. This is called a reaction profile or reaction coordinate diagram. On the x-axis is the progress of the reaction. On the y-axis is just the energy. And so we start off at some energy here. And in this case, we're going to have H2 and ICL. And the H2 and the ICL have to come together in a collision. And when we have a collision, there are two things that we have to pay attention to in a collision. One, we have to look at the orientation and so the H, there are different orientations that they can collide. They might collide like this, perpendicular, or they might collide head-on, or they might collide sideways, or they might have a glancing collision. And so we look at the orientation of the collision. And two, we look at the energy of the collision. If the orientation is good and the energy is there, enough energy to break the bonds, then we have a successful reaction. And so what has to happen, they come together and collide. When they collide, we have to have enough energy to break bonds. That's called the activation energy, E sub A here. It's the amount of energy required to break bonds. But it's not just the bond energies, because at the same time we're breaking bonds, we're forming new bonds. And so what it looks like is this. The HH bond is breaking, the ICL bond is breaking, but at the same time the HI bond is forming and the HCl bond is forming. And so we have bond breakage and bond formation taking place together. This state here, where the bonds are breaking and the bonds are forming, this is called a transition state. And the transition state is not like an intermediate. You know, when I talk about intermediates, intermediates are typically stable. You can see them. This transition state is it's transitioning from the reactants to the product, and it could be an intermediate product. In this case, there is an intermediate product, and the products are more stable. They don't always have to be. I mean, it could be exothermic or endothermic. This is what we call delta H here. And so here we end up forming HI and HCl. Well, HI is an intermediate product. To be fairly stable. I didn't write the lone pairs in there. This reaction is reversible. For example, I could have another collision this way, right? If I have a collision this way, then it could go through this exact same transition state and go back. And so the activation energy in the forward direction is this hill, but the activation energy in the reverse direction, if I were to go backwards, is much more significant. To be for the reverse. But it is a reversible process, so it could potentially do that.
It's more unlikely, given
Yeah.
a bigger gap.
Yeah, because of the high energy. It's less likely because when we look at, collision frequency, when we look at this term here, all right, K, this is going to equal A e to the minus EA over RT. And look at this term here. What does this relate to? This relates to our thermal distribution. And so what we have here is a population versus energy. Do you know what the thermal distribution looks like? Or the speed distribution or the kinetic energy distribution? It looks something like this. This Maxwell-Boltzmann type distribution. Where the bulk of the molecules will have some energy here. But some of these molecules will have fairly high energy. There's going to be an energy cutoff here. The energy cutoff is E sub A. And so there will be a population with energies greater than E sub A and a population with energies less than E sub A. Here. So as E sub A it grows smaller, that is, the amount of energy it takes to form this transition state becomes smaller than the population grows. And so as E sub A becomes smaller, population becomes bigger and K becomes larger. And so the rate will go faster. As E sub A grows bigger, this is to the negative. As E sub A grows bigger, then the population gets smaller and K should shrink. And so the rate constant depends on the magnitude of A. How hard are the bonds to break? The harder the bonds are to break, the slower the reaction is going to be. The easier they are to break, the easier it's going to be. But again, it's not just bond breakage because we're also forming at the same time. And then temperature. Temperature just shifts the distribution, the population up. And so if we increase the temperature, the population of higher energy molecules grows. As we decrease the temperature, the population of higher energy molecules decrease. And so we can see how temperature is going to impact things. The higher the temperature, the bigger the K. The lower the temperature, the smaller the K. So we have that. Okay, I need it a little bit more. Let me extend this out. So this is what we call step one here. Step one is going to be the slowest because it's going to be the biggest barrier to overcome. Step two will be less of a barrier. So we're reacting this with another ICl. There's going to be plus an ICl here. And so these two have to be in the right orientation to collide. That's going to be determined in A. And then there's going to be an activation energy here. The activation energy is going to be smaller. It costs less energy to activate this step. And then this is going to fall to the final products. The final products will be I2 plus HCl plus another HCl, 2HCl. And so here we have step two. And so it doesn't matter how fast step two is, you know, everyone's going to be slowed down by step one, yeah, the biggest activation. And so we have another simple collision here. We generate some kind of intermediate here. You know, the orientation for this collision has got to be like this, you know, where if we have an HI like this, then we want to be breaking the ICl bond and forming the HCl bond and forming the II bond. And so this would be the second transition state here. All right, so this would be K1 over here. This would be K2 over here for step two. And so let's take a look at what K depends on again. K is going to depend on A, EA, and T. And so let's look at a theoretical derivation. Can we get this theoretically without doing any experiments? So theoretically, what, you know, A, you could generate from, you know, statistical analysis of collisions. And so in statistical analysis of the collisions, you take a billion or a trillion collisions and see, you know, how many of those would have the correct orientation and how frequently do those occur. So this would be the collision frequency, A. Then EA, you know, EA is not just bond energy. Now, it's not just breaking bonds, but forming the bonds too. And so in order to determine EA, theoretically, we'd have to know the energy of the reactants, but we'd also have to know the energy of the transition state. And so how do we get the energy of the transition state? So for EA, theoretically, what we do is quantum mechanical calculus. And so we model the transition state. You model the transition state and then you calculate the energy. And that should give us E sub A. This is theoretically. We can also determine these things experimentally. So from experiment, what's typically done is we generate an Arrhenius plot. To generate an Arrhenius plot, we measure Ks at different temperatures. And so K1 would be at temperature 1, K2 at temperature 2, etc. Not necessarily the step, but just K for the same step. And then we'll plot out this. We're going to take the natural log of both sides. ln of K is equal to ln of A e to the minus EA over RT. When we do this, we'll get ln of K is equal to minus EA over R 1 over T plus ln of A. When you look at this equation, it has the y equals mx plus b form. And so we graph the natural log of the rate constant versus 1 over temperature. And we get some data like this, depending on how many data points we have. It should be a straight line where the slope is equal to minus EA over R, and the intercept here is equal to ln of A. And so from the Arrhenius plot, we're able to determine EA and A. Collision frequency. All right, this is for multi-points. Now, for multi-points, you'll want to graph it out. We graph it out, and then we do something called linear least squares fit. A linear least squares fit averages all your experimental data to minimize the random errors, pop up and down. But really, to define a straight line, we only need 2 points. So this is a 2-point analysis. You know, 2-point is fine in theory, but in practice, 2 points could be a little bit uncertain because of random error. You know, if you have only 2 points, then the random error is not averaged out necessarily like in a multi-point analysis, because if you got small fluctuations up or down, you can just average those, draw the best straight line fit. But if you only have 2 points like this, then you might actually be in quite a bit of error. Yeah. But nonetheless, we'll look at a 2-point analysis, assuming the data is good. If we do 2-point, then we use this mathematical trick. And this mathematical trick is to do this. I'm going to skip some steps. We're going to take ln of k at temperature 2 minus ln of k at temperature 1. Well, ln of k at temperature 2 is equal to minus EA over R 1 over T2. And then ln of k at temperature 1 is minus EA over R 1 over T1. So we get something like this. Now, using the property of logs, we'll get ln of K2 over K1 is equal to minus EA over R 1 over T2 minus 1 over T1. And so this is just a 2-point, you know, we don't have to do the graphing because it's just 2 points. And then we can make our life simpler by using this equation here. And so from this, we can determine EA or K2 determination. Sometimes one of the things that helps for this is this ratio, you know, K2 over K1. The K2 over K1 ratio is pretty much the same as the rate. It's going to be directly proportional to the rate of 2 over the rate of 1. If K2 is a lot bigger, you know, let's say K2 is twice as big as K1, then we know the rate should be twice as fast. But it's going to be inversely proportional to the times. And so, related, you know, the faster it is, the less time. You know, so the bigger the rate, the smaller the time. So that's what we'll have here. And so one example is, in talking with rates, is in cooking there used to be a rule, and the rule is for every 10 degrees C temperature increase, the food cooks twice as fast. And so here, this rule is from if we increase T by 10 degrees C, then the rate doubles. So they have, high altitude cooking directions. High altitude cooking directions because water boils at a lower temperature, therefore you need to increase the amount of time you cook. And so let's try this. What must EA be if going from, let's say we went from 80 degrees C to 90 degrees C. So we increase the temperature of the water by 10 degrees C. We want the rate to double. And so what must EA be if 80 to 90 degrees C doubles the rate? So going from 80 to 90 degrees C will cut the time in half or double the rate. And so for something like this, you would use this form, Arrhenius. And why don't you calculate what you get? Well, actually, let's do it. We don't have much time left. That means K2 must be 2 times K1. The rate of 2, given the same concentrations, the rate of 2 must be twice as fast. Does it make sense? And therefore, if we have ln of K2 over K1, this is going to equal ln of 2 times K1 over K1. And so K1 cancels, which gives us ln of 2, which is equal to minus EA over R times 1 over T2. Well, T2 is 90 degrees C, and we have to use Kelvin, so this will be 363 Kelvin, minus T1, which was 80 degrees, and so this would be 353 Kelvin. It has to be Kelvin temperature, because if you plug in 0 degrees C, it's not going to work. R is 8.3145 joules per mole Kelvin. And therefore, EA is equal to what?
This is supposed to be a really big number.
Could be. What did you get?
73,848.
73,848 joules per mole.
Yeah.
Let's see if other people got the same. 73,848 would just be 73.8 kilojoules per mole.
That's what I know.
57,
163.
57.663
63.
joules or kilojoules?
Joules.
You got 73,000?
Yeah. We got 57.
Okay. Let's try this. Let's see what we get. since it looks like a pretty even split, try this here. $73,000? Yeah, actually, that's what I got too, 73,000. Well, what is a typical bond energy, roughly? Okay. You know, a typical bond energy is around, some of the weakest bonds are slightly under 100 kilojoules, like an iodine-iodine bond. And the bond energies are several hundred, 300, 400 kilojoules per mole for a single bond. And so this is quite a bit smaller than your typical, you know, a hydrogen bond is about 25 kilojoules per mole. But it makes sense because when you cook food, you know, are you breaking very strong bonds? No. And so for food, you know, the activation energy is small, but for chemical reactions, the activation energy is typically much bigger. And so for your usual chemical reaction, it probably takes more than a 10 degrees C temperature increase to double the rate. But it's surprising because you don't have to double the temperature to double the rate. You know, you just increase it by some amount that depends on how strong the bonds are, your activation energy. Okay, we'll stop here since we're out of time. Continue.
Yeah.